Today we're going to talk about derivatives of exponential functions. So the derivative of the natural exponential function, if you're taking the derivative of e being raised to a function of x, the e to the function of x will repeat, and then in front of it you will stick the derivative of that power. So this is an application of the chain rule. I do have a little shorthand that I use. If your function f of x is e to a power, then its derivative is the derivative of the power times e to the power. Again, notice this e to the p repeats exactly. We just stick the derivative of that power in front. Let's look at a few examples. What if we just wanted to take the derivative of e to the x? Well, when we look at that, that's e being raised to a power, so its derivative is going to be p prime e to the p. Well, what is e being raised to? What is that power? It's x. What's the derivative of that power? Which is 1. And now we can plug in our p prime and our p, and we get that the derivative of e to the x is 1 times e to the x, or just e to the x. So e to the x is a very special function whose derivative is itself. So the second derivative would be e to the x, the third derivative would be e to the x, so on and so forth. All right, so what if we change it up a little bit? G of x equals e to the 4x minus 1. Again, we're taking the derivative of e being raised to a power, so it's going to be p prime e to the p. So the e to the power will repeat exactly, and we just stick the derivative of the power in front. So what is e being raised to? What is that power? 4x minus 1. What is the derivative of that power? 4. And so we can plug in our p prime and our p, and we get that the derivative of e to the 4x minus 1 is 4e to the 4x minus 1. S of t equals 7 times e to the t cubed minus 10t plus 8. What is that 7? That 7 is a coefficient. Coefficients just carry through and multiply in at the end. They're the annoying little brother that you tag along, and then you just stick it in front at the end and multiply it in. So when I take this derivative, it's just going to be 7 times p prime e to the p. So we can figure out what p is. P is the t cubed minus 10t plus 8. And so then, remember, we keep that e to the p exactly the same. In front of it, we stick the derivative, which is going to be 3t squared minus 10, and then we have this 7 right here. I'll go ahead and distribute that 7 to both terms, and we'll just leave our answer like this. Now, I want you to note that this set of parentheses here and this set of parentheses here are very important, because you're taking the entire p prime times e to the p. If you didn't have this parenthesis right here, then it would look like you're just multiplying it by 10. Same thing here, if you didn't have that parenthesis there, then that e is only being multiplied by the 70 and not the 21t squared as well. All right, let's take a look at this one here. Y equals x cubed e to the 5x. What's going on here? Let's look at it again. Y equals x cubed times e to the 5x. Variable times variable. In order to take this derivative, we're going to have to use our product rule. I'll remind you what our product rule is. Our product rule is the derivative of the first times the second plus the first times the derivative of the second. And remember, you can switch these. You can do the derivative of the second times the first if you'd like. So what comes first? That's everything before the word times. So that's x cubed times e to the 5x. So our first is going to be x cubed. That derivative is 3x squared. And our second is everything after the word times, which is e to the 5x. E to a power, it'll be p prime e to the p. That derivative will be 5e to the 5x. So now I have f prime, s, f, and s prime. I can plug those all in. Now we'll simplify this a little bit. Typically we'll pull that 5 out front here. And then what a lot of people will do is they'll actually pull out that greatest common factor. Notice there's an x squared and an x cubed, so they both have x squared, and e to the 5x and e to the 5x. So the greatest common factor here is x squared e to the 5x. And when I pull that out, I'm left with 3 plus 5x. All right, c of x equals 4x times e to the x squared plus 4e to the negative x plus 4x. So here, 4x times e to the x squared, variable times variable, we are going to have to use the product rule there. Here, that 4 is a coefficient, but that's not just e to the x, it's e to the negative x, so I'm going to do my p prime e to the p. Plus the derivative of 4x is just 4 times the derivative of x, which is 1. All right, so when I do the derivative of the first, 4 times the second, e to the x squared, plus the first 4x times the derivative of the second. That e to the x squared repeats, and the derivative of the power x squared goes in front, which is 2x. Now here, that's going to be 4. Now the e is being raised to the negative x, so the p prime is negative 1, e to the negative x, and then we have a plus 4. Simplify that a little bit. I'll do this 4x times 2x and this 4 times negative 1 to get my 4 e to the x squared plus 8x squared e to the x squared minus 4 e to the negative x plus 4. Now, if you want to pull a 4 out of everybody, you're welcome to, but I'm perfectly happy if you want to leave your answer just like that. All right, find d2y over dx2 if y is equal to 5e to the 5x to the 5th. All right, let's look at this. What does this d2y over dx2 mean? This means differentiate y twice with respect to x both times. In other words, find the second derivative. In order to find the second derivative, you need the first derivative. So when I take my first derivative, that 5 is a coefficient, p prime e to the p. What is the power? What is e being raised to? That 5x to the 5th. So the derivative of that power is going to go in front, 25x to the 4th, and we leave the e to the p exactly the same. So now I can multiply the 5 and the 125 to get that my first derivative is 125x to the 4th times e to the 5x to the 5th. That's my first derivative, but look again, I'm trying to find my second derivative, so I'll differentiate again. Here I have 125x to the 4th times e to the 5x to the 5th. Variable times variable, I'm going to have to use that product rule. The first will be this 125x to the 4th. The second will be e to the 5x to the 5th. Derivative of the first is going to be, bring the 4 down, 500x to the 3rd times the second, plus the first, leave it alone, times the derivative of the second, p prime e to the p. Let's simplify these two together by multiplying them. And then we can pull out the greatest common factor. They're all divisible by 125, and they all have an x cubed, and they all have an e to the 5x to the 5th. So I pull out that 125x cubed e to the 5x to the 5th, and I'm left with 4 plus 25x to the 5th. Don't forget about that product rule. All right, so as you can see, we've done exponential functions. We were taking the derivatives of exponential functions when the base was e, but what if it wasn't e? What if it was like 7 or 2 or 3 or 9 or something to that effect? So the derivative of anything else, a to the x, would be a to the x. It'll repeat just like e to the x did, except we tack on a natural log of a. Now this actually works for e to the x as well, because e to the x, the derivative would be e to the x times the natural log of e. And we know that the natural log of e is 1. So if you really wanted to just use this formula, you could. Now the chain rule will apply here. The derivative of a being raised to a function of x, it's exactly like it was for e, right? P prime times a to the p. We just have to tack on this natural log of a at the end here. So let's look at a few examples of that. If I wanted to take the derivative of 7 to the x, well, that's just 7 to the x, so I'll use this derivative formula right here, a to the x times the natural log of a, and in this case our a is 7. So the derivative of 7 to the x would be 7 to the x times the natural log of 7. Here, if I'm going to take the derivative of 5 to the x squared plus 3, then I'm going to use that chain rule, so that's going to be p prime times a to the p times the natural log of a, where in this case our a is 5, and our function of x, or our power, is that x squared plus 3. So the derivative of that power, x squared plus 3, is 2x, so that's going to be my f prime here, that p prime, times 5 to the x squared plus 3, and then we tack on a natural log of 5. If p was equal to 9 raised to the q cubed minus 5q squared plus 7q minus 3, again, I'm going to use this formula right here. F prime of q times a raised to the f of q times the natural log of a. The derivative of the power times 9 being raised to the power times the natural log of 9. So when I take the derivative of that power, I get 3q squared minus 10q plus 7 times 9 raised to that power times the natural log of 9. And you can just leave your answer just like that if you choose to do so. That's it for derivatives of exponential functions. I'll see you next time.